So it turns out if matrix A can be reduced to a strict upward triangle matrix using only row operation 3, so essentially strict upward triangle matrix is what we get when we do REF. Using only row operation 3, remember row operation 3 is defined as Rx equals Rx plus some multiple of Ry. Keep in mind, some people define it as minus L Ry, so just keep in mind what that sign is. It turns out it's possible to represent this reduction process, these row operations, in terms of a matrix factorization. Matrix factorization just means products of two matrices. That's all it means. Nothing fancy. It's just 6 can be represented as 2 times 3. That's a factorization. Same idea here. We can represent A as the product of two matrices, or L times U, where L is going to be a lower triangle matrix, U is an upper triangle matrix. So U here is going to be REF. That's U. After we do our row operations, we're going to get U. Keep in mind, only row operation 3. So for a 3 by 3, we need to do 3 row operations. Okay, so let's say we have A over here. The first row operation that we would do, once again, it's the same steps every single time. These are the tips and tricks that I taught you with Gauss elimination. We're going to find this 0 here, but we can only use row operation 3. So I'm going to go ahead and say row 2 equals row 2 plus 1/3 row 1. I'm going to use this location here. I can represent this as an elimination matrix. E21 is going to look like identity. We're in the 2-1 position. Row 2, column 1. I end up having my multipliers, so I put a 1/3 here. So this 1/3 goes in the 2-1 position. So if I do this row operation, I can do it manually, or it turns out if I just do E21 times A, it will do that row operation for me. So row 1 doesn't change. This would be a 0, these would be different numbers, etc. So I can represent my row operation as the product of my elimination matrix of that row operation and A. And I can do that for my other zeros as well. So I can go ahead and make this a 0. So I can do E31, so I can use row 1 to do that. What that's going to do is that's going to give me a 0 here. And then lastly, I need to make this a 0. So E32, using row 2. So that would give me a 0 here. So this here is REF, or it's U. It's equal to U. So this multiplication represents my 3 row operations that I can use in order to reduce A to REF. So if we multiply all these matrices together, let's call it E. EA is going to give me U. So in order to get A as a product of 2 matrices, I want to get this E to the other side. So I can say A equals something times U. In matrix math, we can't just divide by E. Remember, we have to do the multiplication of the inverse. And it turns out the L matrix is going to be just the inverse of this E. So A equals E inverse times U, or this here's L, where L is this, where I take the inverse of all my matrices one at a time. And if you remember from the last video, the inverse of an elimination matrix is the same elimination matrix, but the sign on our multiplier changes. So the inverse here, E21 inverse, is the same thing as this matrix, but the 1/3 becomes a negative 1/3. So L ends up looking like this. L always ends up looking like this. We're going to have 1s along the diagonal, and then we're just going to plug in our multipliers. So whatever we use for our row operations is going to be negative 2,1, negative L3,1, and negative L3,2. Once again, it depends on what you define your row operation as. Up here, if you do a minus or a positive. In this matrix here, they're defined, this row operation is defined in a negative. So depends on how you define your row operation. Okay, so if we want to approach LU factorization problems, we are going to do it this way. So first, we're going to solve for row echelon form. We're going to get to REF using only row operation 3. For a 3 by 3, it's these exact 3 row operations every single time. We're going to replace row 2 by adding row 2 to some multiple of row 1. We're going to replace row 3 by adding it to some multiple of row 1. And we're going to replace row 3 again by adding it to some multiple of row 2. If you had a 4 by 4, you would have 6 row operations, but you'd still do the same thing. You'd get all your zeros in column 1 using row 1. You'd get all your zeros in row 2 using row 2. All your zeros in row 3 using row 3. That's essentially the process. It's the same thing I've been talking about with Gauss elimination and Gauss-Jordan elimination. Once we have all of those, keep in mind this is a plus here. Once we have all of those row operations, we're going to go ahead and change the sign on our multipliers and plug into L, where L looks like that. And we'll look at lots of examples, but it's the same process every single time. Same process every single time. That's the nice thing about LU factorization. It's you just follow them blindly. Follow them blindly. That also makes it nice for computers. This is a great algorithm to plug in for computers. That's our first method. There is a second method where we can find LU factorization. What we can do is we know that A equals LU when we say that A is composed of these numbers, A11, A12, A13, etc. And we know what L looks like. L looks like this. I'm going to make them positive. And U looks like this. So if we just go ahead and do that multiplication with our variables, so we just multiply L times U, we end up with this matrix here. And then we can just do equal matrices, where A11 equals this, A12 equals this, A13 equals this, and then A21 equals this. But it turns out we already know what U11 looks like, so we can solve for L21, etc. And you go through and set everything equal to each other. And it turns out every single time you have one variable that's unknown, and you can solve for your one unknown variable given all your numbers. And we'll go through examples like that one too. This one's nice in terms of on paper, if you remember, if you can actually do this multiplication, which you should be able to, but you're working with individual variables. It's not really great for computers. This one is perfect for computers because it's the same steps every time. But that's how we can go ahead and find the LU factorization of a matrix.